In this video, I'll talk about the vector calculus concepts of gradient, divergence, and curl. First, we'll discuss gradient because it's the simplest, and then divergence, and then curl. So the gradient of a function is essentially the multidimensional equivalent of the derivative of a function. So in one dimension, we have x, and then we have a function of x. If we have some function, at this point, we can take the derivative, which is the tangent line. If we think about that as a vector, instead, we have a derivative with a magnitude of approximately 1 and a direction of plus x. So we could think about the derivative here as df dx in the positive x direction. First, this generalizes to 2 dimensions. Here we have a function of 2 dimensions, so the function value is in the 3rd dimension in this drawing. If we take the derivative in both directions at, say, this point, that will give us a vector that points upward. This is the gradient. We represent this with the operator del. So just like in one dimension, we'll have the x component and the y component. And this is the same in 3 dimensions. Del in 3 dimensions is d dx x hat plus d dy y hat. These are partial derivatives plus partial z hat. And the gradient of a function is defined as this operator operating on function. And you can only take the gradient of a scalar function. So it's essentially the 3-dimensional vector derivative of a scalar function. And the gradient always points in the direction of greatest increase of the function value. Now, the divergence and curl are vector derivatives of vector functions. So let's say we have a vector function. First, we'll discuss the qualitative meaning of the divergence and the curl. So the divergence is basically a measure of how much flow is coming out of a point. So if we look at a point on this graph, like first the origin, and we draw a little shape around it, the value of our function is outward all around that shape. So we'll have a positive divergence. Positive is for outward. Now consider like this point over here. If we draw a little shape around that, we have a large outward flow and a smaller inward flow. And so the divergence will still be positive because more flow is leaving the infinitesimally small shape than is entering it. So we can quantify that with the definition of the divergence, which is the del operator dotted with our function. And that equals the sum of the partial derivatives in each direction of the value of the function in each direction, which will be a scalar quantity. The function on the right, b, is an illustration of curl. The curl is qualitatively the rotation of the vector field about some point. So if we pick the origin as the point where we're examining the curl, we can see that there is a lot of rotation going on about this point. Note the expression for the curl will be the same irrespective of any point that you choose, but the curl could still be a function of position, so it could be different at different points, which is also true of the divergence. Quantitatively, the curl can be expressed as the del operator again, crossed with a vector function t. And in this case, this will give us another vector because the cross product of 2 vectors is another vector. And the result will be, so notice that in this expression, the value in each direction depends on the value of the function in the other 2 directions because we're looking at how the directions of the function value are interrelated, hence rotation.